This one is called Otto cycle, and second one we are seeing the diesel cycle. Second one we are seeing the diesel cycle. Why they call as a Otto cycle? That Otto cycle we will call as a Otto cycle, or we can call as a constant volume cycle, and diesel cycle is called as a constant pressure cycle. And today class I am going to explain about the both these cycles. That is a dual cycle. It is called as a dual cycle, or it is called as a semi-diesel cycle or limited pressure cycle. This is the thing: limited pressure cycle, combined cycle, or mixed cycle. Why they call as a dual cycle? The dual cycle means there is a combination of Otto cycle and diesel cycle. It is a combination of Otto and diesel. Since it is two cycles combined, so they call it as a dual cycle or semi-diesel cycle. That is a half of the things we can take it as a semi-diesel cycle. Since it is this cycle, so half of the things will be similar to the diesel cycle, so they call it as a semi-diesel cycle. Then they call it as a limited pressure cycle, because that cycle pressure, maximum pressure is limited. So they call it as a limited pressure cycle or combined cycle. Since they are going to combine Otto cycle and diesel cycle, they call it as a combined cycle. And mixed cycle. Mixed cycle means again they are going to mix both the cycle Otto and diesel. We have the various names. I have taken this thing from the various book. If they give us a mixed cycle is called the dual cycle, or if a semi-diesel is called a dual cycle, or limited pressure, everything is called as a dual cycle. So similar to last class, we are going to see first what is a PV diagram. So only difference the Otto and diesel, that heat supply will be in the Otto cycle will be in the constant volume cycle, and diesel cycle heat supply will be constant pressure. So here, since it is combined, we are going to combine heat supply will be constant volume as well as in the constant pressure. So if we take this as a heat supply, we have the constant volume as well as in the constant pressure, and heat rejection always will be a constant volume. So I have written that vertical line. So PV, the y-axis is pressure and x-axis is volume. So that process 1 and 2 is reversible adiabatic compression process. This is state 1 and state 2, where process 1 to 2 is called reversible adiabatic compression process. Where reversible adiabatic can call as a isentropic process. This is called the isentropic compression process. Now then process 2 to 3 will be heat supply at constant volume. This is state 3. That process 2 to 3 is a heat supply at constant volume. So we can write that 2 to 3 process is heat supply at constant volume process. Then process 3 to 4 will be a heat supply at constant pressure. You can take that 3 to 4 is heat supply at constant pressure process. That 3 to 4 is where parallel to x-axis, that is a perpendicular to the y-axis, that is a constant pressure, where P3 equal to P4. Then 4 to 5 there is a expansion, isentropic expansion. This is a process you can take as a expansion process. This is state 5. That 4 to 5 you can take as a reversible adiabatic expansion, and 5 to 1 will be heat rejection. 5 to 1 is heat rejection at constant volume. So now we can observe now only that variation, that Otto cycle and diesel cycle. If we take this thing 1, 3, 4, 5 will be a diesel cycle, because heat supply will be a diesel cycle, constant pressure in the diesel cycle. But in the Otto cycle, heat supply will be in the constant volume. Since we are going to combine Otto cycle and diesel cycle, it is called as a combined cycle or dual cycle. Since both the cycles are involving, they will call as a various name. Now we will go for the efficiency. We will go and derive the equation for the efficiency. We know that efficiency equal to always output by input. What is the output? So output is, we are going to get work done as a output, work done by heat supply, where work done equal to heat supply minus heat rejection divided by heat supply, where we can write 1 minus HR divided by HS, where HR equal to heat rejection, HS equal to heat supply. So now we will write the equation for the heat supply and heat rejection, where heat supply will be equal to mCV, because we have the first, we are going to supply the heat in terms of constant volume. So we have to, since it is constant volume, we have to substitute the C suffix V, that is a specific heat at constant volume. Then what is the maximum temperature? T3 minus T2 plus mCp, because that process 3 to 4. Process 3 to 4 is heat supply at constant pressure. So we have to substitute the Cp, and the temperature difference is T4 minus T3. So before that we will draw the TS diagram also. Temperature based entropy diagram, where process 1 and 2 is reversible adiabatic compression, that is called the isentropic. So we can call it as a, since it is isentropic, we will have the vertical line. 1 to 2 is reversible adiabatic compression. So entropy will be remain constant, S1 equal to S2. And 2 to 3 process heat supply, so that entropy will be increased. This is a process 2 to 3, where here heat supply at constant volume. So up to this. Again 3 to 4. So 3 to 4, just state 4, this is a heat supply at constant pressure. Then 4 to 5, and we will come back to initial state. This is a heat rejection at constant volume. So now we have written the equation for the heat supply, where heat supply equal to mCv T3 minus T2 plus mCp T4 minus T3. Similarly, we can write the equation for the heat rejection, where heat rejection equal to mCv, because heat rejection will be in the constant volume process. So mCv, what is the temperature difference? T5 minus T1. T5 minus T1. Then we can substitute heat supply and heat rejection in the efficiency equation, that is 1 minus HR divided by HS. So efficiency equal to 1 minus, where heat rejection equal to mCv T5 minus T1 divided by heat supply will be equal to mCv T3 minus T2 plus mCp T4 minus T3. So in this we can take mCv, the numerator, so denominator also we have mCv, we can take mCv outside. We take mCv outside, we will have 1 minus mCv T5 minus T1, and I have taken mCv outside, then we have T3 minus T2 plus, since I have taken a m outside, Cv I have to take outside, then it will become the Cp minus Cv to T4 minus T3. Is it? Sorry. So now we know that Cp by Cv equal, that is a specific heat ratio, Cp by Cv equal to gamma. Then we can write efficiency equal to 1 minus T5 minus T1 divided by T3 minus T2 plus gamma into T4 minus T3. So this is a equation, efficiency of the dual cycle in terms of temperature. So now we have to derive the equation of the efficiency in terms of cutoff ratio, compression ratio and expansion ratio. So for that, what we will do, we will take all the temperatures T2, T3, T4, T5 in terms of T1, then we can substitute here, we can take T1 outside, we can simplify it. So for that I am going to take the process, first process 1 to 2. 1 to 2 process is called reversible adiabatic compression process. 1 to 2 process is reversible adiabatic compression process, where we know that temperature and volume relations T2 by T1 equal to V1 by V2 power gamma minus 1, where V1 by V2 equal to, what is that? Similar to the previous class, that diesel cycle and Otto cycle, V1 by V2 equal to RC, that is a compression ratio. So we can write T2 equal to RC power gamma minus 1 into T1. So now I have derived the equation for T2 in terms of T1 with RC power gamma minus 1 T1 equal to T2. Similarly we can write the T3 in terms of T1. So we can, for that we can go for the process 2 to 3. process 2 to 3 is heat supply at constant volume. So we can write the ideal gas equation for the state 2 and state 3, where P2 V2 by T2 equal to P3 V3 by T3. So this is the ideal gas equation for the state 2, this is the ideal gas equation for the state 3. Since it is constant volume process, V2 will be equal to V3, then I need to calculate what is T3, so we can write P3 divided by T2 equal to P3 divided by P2. Since it is constant volume process. Yeah. So now we can write T3 equal to, what is P3 by P2? That P3 by P2 is called the pressure ratio. During the heat addition, what is the change in pressure is called the pressure ratio. So this is a state before heat supply. These are point 3. State 3 is called the pressure after the heat supply. So now we can take P3 by P2 equal to pressure ratio, that is R suffix V into T2, where T2 already we have calculated, so we can write T3 equal to RP into RC power gamma minus 1 into T1. So now I have calculated T3 also in terms of T1. Now T2 and T3 I have finished, then I need to calculate what is T4 and T5. So for the T4 and T5 we can go for the process. What is the next process? 3 to 4. So process 3 to 4 is called heat supply at constant pressure. Heat supply at constant pressure. So similar to process 2 to 3, we can write the ideal gas equation for the state 3 and state 4, then we can equate. So ideal gas equation for the state 3, P3 V3 by T3 equal to P4 V4 by T4. Since it is constant pressure, P3 equal to P4 we can cancel, then we can write T4 by T3 equal to V4 by V3. So I need to calculate what is T4 in terms of T1, so I written in the left hand side. So T4 equal to, what is V4 by V3? So during the heat addition, what is the change in volume? During the heat addition, what is the change in volume is called the cutoff ratio. So during the heat addition, what is the change in pressure is called the pressure ratio. What is the during the heat addition, what is the change in volume? That ratio is called the cutoff ratio. So V4 by V3 equal to for RCO, R suffix O. So we can write RCO, where CO equal to cutoff into T3, where T3 already I have calculated. So T4 equal to RCO into RC power gamma minus 1 into T1. So now I calculated T4 also in terms of T1. Then I need to find what is T5 in terms of T1. For that we can go the process 4 to 5. We can take the process 4 to 5 is reversible adiabatic expansion process. Reversible adiabatic expansion process. Where I need to find out what is T5. So T5 by T4 equal to V4 by V5 power gamma minus 1. Where we know the expansion ratio, what is the change in volume during the expansion? So where we know that V5 by V4 equal to R suffix E, where R suffix E equal to expansion ratio. Expansion ratio. So now we can substitute here, since in the equation we have the V4 by V3, so we will get as a reciprocal T5 equal to 1 by RE power gamma minus 1 into T4. So also we know that one more expression when I am explaining the diesel cycle, where compression ratio will be equal to for cutoff ratio into expansion ratio, where this V2 by V1 by V2 will be equal to V5 by V4 into V4 by V3. So if we take V1 by V2 will be equal to V5 by V4 and V4 by V3. That is the expansion ratio into cutoff ratio. So from that we can write that expansion ratio equal to RC divided by RCO. RC divided by RCO. So instead of 1 by RE, I am going to write instead of RE, so T5 will be equal to, so RE is denominator, so we can write it as a RCO in the numerator. RCO power gamma minus 1 divided by RC power gamma minus 1 into T4. So T4 already we have calculated, where RCO into RC power gamma minus 1 into T1. So now this RC power gamma minus 1, RC power gamma minus 1 will get cancelled. Sorry, we have missed that things. T3 we have the RP. We have not included that RP. We have to write this RP. It should be RC into RP. The substitute here it will become this RP also will be in 1, RP into T1. Now here in the numerator we have the RCO power gamma minus 1, RC power 1. So base is same, so we can add it. Then T5 will be equal to RCO power gamma into RP into T1. Okay. So now I got the equations where T2 in terms of T1, where RC power gamma minus 1 T1, and T3 equal to RP into RC power gamma minus 1 T1, and T4 equal to RCO into RC power gamma minus 1 into RP into T1, where T5 equal to RCO power gamma into RP into T1. So all the temperatures in terms of T1, then I can go to the main equation in terms of temperature efficiency, where efficiency equal to 1 minus the numerator T5, that is T5 equal to RCO power gamma into RP into T1 minus T1 divided by T3. T3 equal to, what's your value? RP into RC power gamma minus 1 into T1 minus, we have the T2. T2 will be equal to RC power gamma minus 1 into T1. This is a one term, plus we have the gamma, so we have to add that gamma into T4. T4 will be equal to RCO into RC power gamma minus 1 into RP into T1. The terms will be very lengthy. Then T3 will be equal to again RP into RC power gamma minus 1 into T1. So this is terms 1 minus of this. Then in this, the numerator also, denominator we have the T1 common terms. Here also we have the common terms we can take outside, will get cancelled. And I am going to write the equation without T1. And in the denominator we have the common terms, that is a RC power gamma minus 1. We have the denominator we have the 4 terms, that is RC power gamma minus 1, RC power gamma minus 1, RC power gamma minus 1, RC power gamma minus 1. So we can take the denominator, this RC power gamma minus is common, we can take outside. Then I can write the final equation 1 minus, so if T1 is common, we can take outside, it will get cancelled. Then RCO power gamma into RP minus 1 divided by, so RC power gamma minus is common for all the terms, so I can take outside. RC power gamma minus 1 is common, I have taken outside. Then we have the RP, T1 we have taken outside, minus RP minus 1, RP minus 1. In this term, the second term, denominator second term, we have the RCO and, sorry, RP is common. RP is common, you can take outside. So, plus gamma, you can take, RP is common, we can take outside. I have taken RP is common here. Then we have the RCO minus 1. Is that term? So, this will be our final equation, where efficiency of the dual cycle will be equal to 1 minus RCO power gamma into RP minus 1 divided by RC power gamma minus 1 into RP minus 1 plus gamma into RP into RCO minus 1. So these equation, remembering these equations is very very difficult. For Otto cycle, easily we can remember Otto cycle efficiency equal to 1 minus 1 by RC power gamma minus 1. This for the Otto cycle. Even in the diesel cycle also we can able to remember where we have the term for diesel cycle will be equal to 1 minus 1 by RC power gamma minus 1 into RCO power gamma minus 1 divided by RCO minus 1. So this will be a term for the diesel cycle. So anyway, only Otto cycle equation you can remember it. Remaining due and diesel cycle is very difficult to remember. So whenever you are solving the problems, you can remember that heat supply divided by heat rejection. Efficiency equal to work done by heat supply. So we can individually we can calculate what is the heat supply and heat rejection. So to calculate the heat supply and heat rejection, we should know all the temperature. So for the temperatures only I have taken T2, T3, T4, T5 in terms of RC and RCO. So if you are just off it enough.